Here I have 3 rubber bands. Okay, the red rubber band has been stretched to a length that would support 6 dominoes. The yellow rubber band to a length that would support 8 dominoes. And the blue rubber band to a length that would support 10 dominoes. Provided that all the dominoes end at the black X here. I don't know if you can see the black X, but there's a black X there. And if I support those rubber bands lightly with this paper clip, and this might be difficult for you to see, I don't know, we find that the whole system is in balance when the 3 rubber bands do meet near that point. If I move the system over here, it's going to want to move back. If I move it down here, it's going to want to move back to this point. Wherever I move it, it wants to move back to this point. Now we're going to use vectors to understand what's going on and how we can analyze it. So, I've got a picture here, okay? I've got a vector A of magnitude 6 at an angle of 270 degrees. That corresponds to the red rubber band that was stretched out to a length that exerted a force sufficient to hold up 6 dominoes. The vector B has a magnitude of 8, angle 180 degrees, corresponds to the yellow rubber band whose length is sufficient to support 8 dominoes. And a vector C of magnitude 10, the length is such that it exerts a tension equal to the weight of 10 dominoes at 30-degree angle. Now, I haven't measured the angles of these things. I don't know if 30 degrees is correct or not. Actually, I do. I know what the angle ought to be. And we'll see if it should be 30 degrees. So we just estimate that the blue vector, the blue rubber band, was at an angle of 30 degrees relative to the horizontal direction, which we take to be the x direction. Now we can quickly and easily calculate that a sub x is 0, a sub y is negative 6. We don't even have to calculate that. It's clear that the a vector has only a component in the y direction. It has 0 component in the x direction because it's vertical up and down. And the b vector correspondingly has an x component of negative 8 and a y component of 0. It should be clear why that is so. The c vector, well, it has magnitude 10 at 30 degrees, so the x component of its force is 10 times the cosine of 30 degrees, or 8.7, corresponding to the force that would support 8.7 dominoes. The y is 10 times the sine of 30 degrees, which is 5. Now I've written something down here, here, and here with these I and j vectors. Let's talk about that for a second. You might well know that, but let's go ahead and define it. Here we have a unit circle of radius 1, and from the origin we take a vector from the origin out to that circle along the x-axis. That'll be our I vector. That's going to be a vector of magnitude 1 because we're on a unit circle. It's 1 unit from here to here. And j being a vector in the y direction, having magnitude 1. So there's a picture of the I and j vectors. Now the scale of the unit circle, well, let's not get into that. Let's just accept it for what it is here. Okay, so since ax is 0, ay is negative 6, we can write a as 0 times the I vector, nothing in that direction, minus 6 times the j vector. The j vector is 1 unit, goes 1 unit upward. We multiply it by negative 6, we get a vector with a magnitude of 6 units downward. Similarly, b could be written as negative 8i plus 0j, and c as approximately 8.7i plus 5j. Now let me comment that I'm kind of suppressing the units. We could say that A has a magnitude of 6 domino weights, B a magnitude of 8 domino weights, C a magnitude of 10 domino weights, and then we'd put domino weights next to every magnitude here. But and we will often do that in this course to be sure that our calculations make sense. But for right now, we're not going to do that. Now, we're going to let R be the vector that is the sum of the A, B, and C vectors. So the question is, what is the vector R? And there are two ways, at least two ways, to express the vector R. We could express it in terms of its components, perhaps using the I and J vectors, or we could express it in terms of its magnitude and its angle. We're going to do both. But the easiest way to calculate the vector R is to use the notation we've already got and represent A as 0i minus 6j, B as negative 8i plus 0j, C as 8.7i plus 5j. And we just put plus signs between these things, and we treat these quantities as algebraic quantities. I and j being unlike quantities, so they can't be added, but the I components, 0i and negative 8i and 8.7i, can be added. So without going into the details of why vector addition works the way it does, your textbook will explain that to an extent, and you actually, in prerequisite courses in trigonometry and so forth, should have encountered this. If you haven't, what we're doing here ought to be sufficient. But let's go ahead and do it. Okay, so what I'm going to do is the same thing I would do if these were algebraic quantities. We've got plus in front of each set of parentheses. I can remove the parentheses. I can use associative and commutative laws, which apply here, to regroup everything. And I'm going to get 0i minus 8i plus 8.7i, and then minus 6j plus 0j plus 5j. Now I can factor I out of these three expressions, and I can factor j out of these three expressions to get 0 minus 8 plus 8.7i plus negative 6 plus 0 plus 5j, and that equals 0.7i minus j, minus 1j, and we'll just write that as minus j. Now, I is your vector in the x direction, j is your unit vector in the y direction. And from this we very easily conclude that Rx, the x component of R, has to be 0.7, and Ry is negative 1. So we can express this resultant vector R as 7i minus j. We could express it by simply saying Rx equals 0.7, Ry equals negative 1. But we also want to express it by saying what the magnitude and angle of the vectors are. So we need to specify the magnitude and angle of the vector to express it in that manner. So, well, the magnitude and the angle are found very simply by the, just from the meaning of the arctangent and the Pythagorean theorem. We get these formulas and we apply them, and we see that first of all, R is square root of 0.7 squared plus 1 squared, which is the square root of 1.49, and that's going to be approximately equal to, and I'm doing this in my head right now, but 1.44 is the square of 1.2, because 144 is the square of 12, and we can interpolate between that and 1.3 squared, which is 1.69, and we're going to probably conclude that this is approximately equal to about 1.22, maybe 1.23. The arctangent of Ry over Rx is going to be the arctangent of negative 1 over 0.7. Notice I didn't bother writing the plus 180 degrees if the x component is less than 0, and that's because the x component is greater than 0. We always want to consider if the x component here is less than 0, we're going to have to add 180 degrees, or if we're working in radians, we add pi radians. Now, I'm not going to go into a lot of detail trying to estimate the arctangent of negative 1 over 0.7. Negative 1 over 0.7 is about 1.4. I know the arctangent of 53 degrees is 8/6, which is 1 1/3, 1.33. I know the arctangent of 60 degrees is the square root of 3, 1.732. This is quite a bit closer to 53 degrees than 60 degrees then, so I'm going to estimate that that's maybe 55 degrees. And you can, of course, take your calculator and very easily get that arctangent. Now, I got wrapped up trying to estimate the number. It's actually, if you put it into your calculator, you're going to get something close to negative 55 degrees. Well, that's closer to 54 or 56. I don't think it's very far from 55. Now, of course, negative 55 degrees, that would indicate 55 degrees measured in the negative direction from the positive x-axis. That's going to be a vector down here. And, of course, if you draw a vector with an x component of 0.7, y component of negative 1, it's going to be in your fourth quadrant. We can do the equivalent angle, negative 55 degrees plus 360 degrees, which is 305 degrees. Okay, just a demonstration of how we can move from our circular definition of the trig functions to an analysis of a simple force diagram.